Chapter 8 is all about chain rule. Chain rule is the last of differentiation rules and will complete our collection that so far consists of sum rule, difference rule, product rule, and quotient rule. Let's think about functions in general first. So if I were to take derivatives of any one of these, I have to think of the algebraic structure of the function, so I'm able to decide what differentiation rule to apply to the scenario. So for example, this first function is a sum of two functions, so I will be applying the sum differentiation rule, which essentially says that I can take derivatives of the functions that compose the sum separately. The second function here is, of course, a product, and therefore, if I were to take a derivative of it, I would have to apply the product rule. This next one is a quotient, which will then call for quotient rule. And what about this last one? So inside of the seventh power, it's a sum, but outside here, it's the power. So how can I classify this function? Is it a power function? Is it a sum and then a power? Well, this is essentially exactly the problem, is that this function is a composition of more functions than just one. And we need to be able to break it back down in order to figure out what its actual structure is. So this is going to be an incredibly fast review of function composition. If you need more of a refresher, please go take a look at the pre-calculus review package. There's a section on function compositions. Generally, function composition, we think about it as a one step at a time process. So let's take a look at this function, x plus 3 all squared. If I were to give you a particular value of x, what would be the first operation that would be applied in calculating x plus 3 squared? Well, first of all, you will be adding a 3. So the first function that gets applied is an add 3 function. And the output here will then be x plus 3. And then once we have that computed, we will raise the whole thing to power 2. So the next function that gets applied will be to square it function. And result here will be x plus 3 squared. Now, as opposed to giving them verbal names like add 3 and square, I can also give them much shorter names so that I can use the function notation. So let's say the add 3 function will be called f, and the square function will be called g. Then we notice that if I were to rewrite x plus 3 squared, what happened to x first, so let me write on this right-hand side here, is I took my x, and the first function I applied to it was the function f. So the first thing to act on x was f, and then once I had the output for that, I applied the function g to it. So afterwards, we applied g. So notice that the functions here get applied from inside out. I start with x, and then I build up layers of functions on top of it. The order here matters a great deal because g of f of x is not going to be the same as f of g of x. So in this case, for example, f of g of x means that I first took x and applied the g function, which was to square it. So first I had x squared, and then I had to apply f to it. So my outcome here will be x squared plus 3. Now, of course, x squared plus 3 is not the same as x plus 3 squared. So the order in composition really matters. The other thing that I should mention here is the notation that we use for function composition. So writing this out is a full way to write this out in function notation. The other way to write this out, so for example, if I have f of g of x, is to use this little circle in the middle. So this is what we would read as f composed with g of x, or f of g of x. Okay, so with this in mind, the chain rule states that if I were to take a derivative of a composed function f of g, I have to take a derivative of the outside first, followed by the derivative of the inside. So I tend to think about that as an onion. If you're peeling an onion, you're going to have to take an outside layer first, but the inside stays put. So it's the same thing here. I take a derivative of the outside function, but the inside function stays the same. when you're taking the top layer of your onion off, you cannot affect the middle of the onion. The middle stays the same. But once the top layer is off, you have access to the middle, so you proceed to then take a derivative of the middle. So this is generally going to be how chain rule works too. We're first going to take the derivative of the outside function, keeping in mind that the inside stays the same, and then follow by taking the derivative of the inside function. So in all of the chain rule problems, the first and the key step would actually be to determine what is the outside function and what is the inside function. So far, we have only worked with polynomials, and with polynomials, it's actually going to be fairly easily to figure out what's inside and what's outside. So here, if you have to think of how does the composition occur, so if I did pick a particular value for x, and I went through to actually calculate this expression, then the first thing that is going to happen to x is I'm going to compute the value for x squared plus 5x. So this is my inside function. And once we've computed that, we're going to raise everything to power 7. So that will be our outside function. It is helpful here too that the inside is physically on the inside of the power. So in this case, it is quite visible. We will see some slightly more obscure examples very shortly. Okay, so according to the chain rule, I have to first take the derivative of the outside function while keeping the inside intact, and then take a derivative of the outside function. So let's do this carefully. So my derivative is, first I take derivative of the outside function. Outside function is the power 7. What is the derivative of something to power 7? So in particular, what is the derivative of x to power 7? Well, this is just power rule, so this is 7x to power 6. So it's going to be the same thing here. The power rule tells me that I need to take the power, bring it down to the front, and reduce the power by 1. But keep in mind that the inside of that function has to stay what it was. So I'm going to bring the 7 down and reduce the power by 1, but the inside has to stay put. And the inside was x squared plus 5x. Okay, so this is the derivative of my outside function. And then I haven't dealt with the inside yet, and now is the time to do so. Once you've taken that outside layer off, we have access to the inside, so I now have to follow by the derivative of the inside function, right? So now is where I look inside. The inside is x squared plus 5x, and so I take a derivative of that, which is 2x plus 5. So this is the derivative then of the inside function. So let's take a look at a couple of other problems, some of them which will involve other differentiation rules that we've already covered up until now. So the first function here is the same as on the previous slide, but then we have functions that somehow build up on it. So 4 times the same function, and then 4x times the same function. So what are we going to do now? How are we going to take a derivative of this now? It is no longer just one inside and one outside. There's also this factor of 4 present up in the front. So it's useful to remember here the constant multiple rule. If I have a constant times a function, then I can leave the constant alone and take a derivative of the function. So this 4 can stay there, and then I just need to take a derivative of whatever remains. Now in this case, that's lucky because this is the exact same function, so as above. So my derivative can be taken from there. So if I were to write this out fully, this would be 4 times 7x squared plus 5x to the 6 times 2x plus 5. There we go, squeezed it in. Okay, the next case is 4x times this function. So in itself, this big function is actually a product of 2 things. So this is one key thing to notice right away, is that if it's a product before it's a chain rule, then I have to apply the product rule first. So here I have a product of 2 functions. So the first rule I have to apply is the product rule. So the derivative of c here would be, recall the product rule is, it's the derivative of the first function times the second function plus the first function times the derivative of the second. Okay, and once you have that, the derivative of 4x is just 4. This stays the same. Then we have 4x, and then we have a derivative of this function that will require us using the chain rule, but it's the same function as above. So we already know how to do that. Okay, so I'll leave it up to you to fill in the next line. Same idea for the next question here is that, first of all, it's a product of two functions. So the first thing I'm going to do is apply the product rule on the two separate pieces. But then my two separate pieces, the first one is just x squared, so that's fine. I can take a derivative of it when I have to. But the second one is 1 minus x all cubed. So the second piece in itself has an inside and an outside, right? So this is then the outside function on that portion, and this one is the inside function of that. Okay, so going through with this, I'm going to write out answers in a second, but please pause here and actually think about what you would get as the answer. Okay, so this is actually the outcome. This is the derivative of x squared followed by the function as per product rule, plus x squared left alone followed by the derivative of 1 minus x all cubed, which is a chain rule. So the power came down, got reduced by 1, while keeping the inside intact, and then I have to follow by the derivative of the inside. The derivative of 1 is 0, the derivative of minus x is minus 1. So this is where this factor of minus 1 comes in. Okay, and for the last question here, again, first take a look at it and figure out what kind of function is this. In this case, it looks like a quotient, so you can apply the quotient rule. That's one way to go. The other thing to maybe notice is that while it's a quotient, the top is just a constant. So I can actually rewrite this whole thing as a power. So it's the power of a cube root on the bottom. The cube root itself is a power of 1/3. It being in the bottom means it's negative. So this whole thing is actually equal to x squared plus 6 to power minus 1/3. And then I can, depending on which route you chose, you can either proceed with the quotient rule or you can proceed with a power rule on this function. Now, of course, the power rule in this case will also involve this as the outside function and this as the inside function. This is a really great example to practice on, so please continue the work here to actually get the final answer. Now, these are just mathematical functions, but chain rule is extremely useful in applications and actually arises quite naturally. So let's take a look at the first one. The population of wolves depends on the population of elk. The elk population, in turn, depends on the abundance of vegetation, which in its own turn depends on the amount of rain of any given year. So you see how this chain of events or chain of dependency is built through the natural cycle of life. We would like to quantify the rate of change of carnivore population with respect to rainfall. So keywords being here, rate of change, which means that we're talking about a derivative. But before we have something to take a derivative of, we need to actually find what that function is. So let's work through this chain. So I have that the wolves depend on elk, which depend on vegetation, which depend on rain. So wolves population is actually a function of elk population. The more, let's say, elk, the more wolf there are. Elk depend on vegetation and so on. So in function notation, I can write this as W of E of V of R. And now I just have to make sure I have enough brackets closing. I think that's about right. Okay, so this is the full chain of dependencies in this situation. The chain rule is called that because you take derivatives in this specific chain, right? So if I were to take a derivative of this function now, so let's say I am taking this function in this function notation, and I would like to take a derivative of it. The chain rule says that you first take a derivative of the outside most function while keeping the inside, and then proceed to work your way in. So the outsidemost function is w. So I will first take a derivative of w and keep whatever inside it has. I'm going to leave it blank for now so I don't have too many letters. So first I take a derivative of w, then I have to take a derivative of e while keeping whatever inside it has. And then next I have to take a derivative of v while keeping whatever inside it has. And now I'm out of variables, r, right? That's kind of like my x in the previous example. I can follow up with r prime here, but that's just going to be 1. Okay, and now that I can clearly see the structure, I can fill in the blanks with the insides of the corresponding functions, just to make sure that I didn't lose anything in the process, right? So the inside here will be e of v of r, which is the inside of the original w function. The inside of e prime will be the inside of the original e function. So this will be of v of r, and the inside of v prime is just r, okay? So this is the entire derivative and how you would take it. Now, the problem is this notation is not only now looking pretty bulky, but it's also making one fact really not clearly articulated, and that is the fact that when I take a derivative of w here, what am I taking it with respect to? Now, the thing in our chain of command here says that w, the wolves, depend on e, the elk. So as far as w is concerned, its independent variable is e. So when I take a derivative of w here, I am doing so with respect to the elk population e, okay? But because all of these variables are present on the inside of the w, it might be difficult to track that. So this is also where the other notation for derivatives might come in much handier, as it would in actually many word problems. So instead of stating the derivative the way that we did, I am going to use the notation that we've discussed earlier, which is df by dx notation. So in this case, I would like to quantify the rate of change of carnivore population, which are wolves, with respect to rainfall, which is r. So this notation makes it immediately clear what is it that I'm taking a derivative of, and what is it that I'm taking a derivative with respect to. And now the chain rule tells me that I have to go through all the layers of my chain to get from w all the way down to r, okay? So the first step here is I'm going to take a derivative of w with respect to e, its independent variable. So the first derivative is w with respect to elk population. And then the chain rule is a chain of multiplications. So followed by times, and then I follow through with the chain. So now I'm at e, I have to take a derivative of e, and its variable is v. So I have to take a derivative of e with respect to v. And now I'm at the v step, so I'm right here. I have to take a derivative of v with respect to r. And this brings me to the end of my chain, so I know I'm done, okay? So this is what the derivative would look like in this notation. The other thing that's actually really easy to check here, I mean, there's lots of really good reasons to actually use this notation as opposed to this one. For word problems, this notation will much easier let you know what the units are, because you have naturally the numerator and denominator, so you will be able to read off the units for the numerator variable and the denominator variable, but also, particularly in the chain rule, it will really let you know if you've done it right. Because in the end, look, if you treat it for a second like quotients, that they are in the limit, then you can notice that, for example, this DE and this DE cancel. They don't quite cancel, you can't actually cancel them out because each one of those things is a derivative and not a real quotient, but at least in terms of units, you can follow this logic. So the two DEs cancel out, the two DVs cancel out, and all you have left is dW by dr, which is exactly the thing that was required on the left. So you can make this sort of common sense check to make sure that you've actually covered all the steps of the chain correctly, which is something that you cannot easily trace through the prime notation here.